What's up, mathematicians? Justin here, and in this lesson we'll be looking at constructing and proving perpendiculars. So before we can construct a perpendicular, we need a line to make the perpendicular to. So the first one we're going to do is called the perpendicular bisector. And so let's go ahead and draw a line here. I'm not going to make it too big, so I'll just kind of put it in the middle here. All right. So there's my line. And we want to draw a perpendicular bisector of this line. Now, first of all, we of course need to know what perpendicular means. Perpendicular just means at a right angle to. So it's a line that will divide this line in half, and it will be at a right angle to this line. It'll be perpendicular. And so if you haven't given it a shot, if you haven't tried to do this construction on your own, I would say pause the video, try it out first, and then I'll do the construction for you. All right, welcome back. So it turns out that this construction is actually the same as the previous one. Let me find it a second here. So this line bisector is also a perpendicular bisector. But just in case you didn't see that video, let's do it really quickly here. I'm not going to do all three. I'm just going to do one. And so what we want to do is we want to set our compass to be the length of this line here. And then we're going to draw an arc like this. And then I'm going to put my compass on this side. Draw an arc like that. Okay. Now, take my straight edge and I connect a line. I draw a line from this intersection point up here to this intersection point down here. Okay, so what does that look like? So here is our perpendicular bisector. So what I'm claiming is that this length is equal to this length, and this is a right angle. So let's do a proof for this real quickly. It'll actually build on the proof from the previous lesson, so it won't take too long. And in fact, why don't I just do it on the same page? You know, why not? Why do all that writing again? So we'll use the same diagram, but I'll add a new given and a new goal. So if you recall from the previous lesson, we had the line AB, and we proved that CD bisected AB. Now we need to just add a couple steps. So we're still given the line AB. Oops, sorry about that. We're still given the line AB. I'm just going to add a different goal. So now next goal is to show that this CD is perpendicular to AB. So show CD is perpendicular to AB. And hang on, I'm going to pause the video and redraw this diagram so that I don't have to keep going up and down. Okay, so let's finish up this proof. So from the proof for the line bisector, you'll recall that we already showed that the triangle ACE is equal to the triangle BCE. So let's start out by repeating that statement right there. So secondary proof to prove that this is actually a right angle is going to start with that statement. So ACE, triangle ACE is equal to the triangle BCE. Okay, and this follows from the steps above. Well, since this triangle is equal to this triangle, we can then say that this angle CEA is equal to the angle CEB. Okay, so these two triangles are equal, therefore these two angles are equal. And the justification for showing these two triangles are equal was SAS. So I'm going to put SAS there. SAS is basically an assumption that says if the side, the angle and the side are equal to the corresponding side, angle, and side of another triangle, the two triangles are equal and all their, everything about them is equal, right? Their measurement, all the measurements, the area, the lengths, the angles, everything is equal. So now that I know that these two angles here are equal, and I'm going to go ahead and write it with a perpendicular because I know they're also perpendicular. So those two angles are equal. Well, we also know that the angle CEA plus the angle CEB, they add up to 180 degrees. How do we know that? Well, you may have heard that a straight line is 180 degrees. That might not be the most precise way to put it, but the definition of the straight angle, I'm going to say definition of straight angle states that if you have angles, an angle or angles that make up a straight line around some point, that's going to be 180 degrees. So these two angles add up to 180 degrees. Okay, well, since they're equal and since they add up to 180 degrees, then we'll say step 4, the angle CEA is equal to the angle CEB, which is equal to 90 degrees. Our justification for that, I'm just going to put arithmetic because we can use arithmetic to determine that half of 180 is 90. So if the two are equal and they add up to 180, then each of them must be 90. And I should probably put that here as well because I didn't say anything about arithmetic or algebra. So I'm actually going to add this to my other assumptions. I'm going to say, okay, not only am I assuming side, 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 angle, side, angle, side, I'm also going to be assuming the things that you've learned in previous classes about arithmetic and algebra. So we won't reprove arithmetic and algebra. I don't know if you proved it the first time, but we're not going to worry about proving it now. We'll just go ahead and accept the facts of arithmetic and algebra. And so, well, since they're equal, then step 5, CD is perpendicular. So I'll say CD is perpendicular. Remember this symbol right here means perpendicular to AB, and that's by the definition of perpendicular. Okay, and we're done because our goal was to show that they were perpendicular, and because they're at a 90-degree angle to each other, definition perpendicular says that they are perpendicular. So once again, I finished part 2 of this proof. Okay, so in the next video, we'll look at how we can construct a perpendicular through a specific point on a line.